Hi everyone, I hope you're having a wonderful day. Today I just wanted to make a quick video on closures as an introduction to them, and I wanted to cover what closures are, and to explain that a bit better, I want to cover what free variables are, and also what scope is. Then once I've done this, we can move on to our first closure, and then I'll show a few examples of how closures can actually be used in practice. So what is a closure? Sometimes it's called a closure, other times a saved lexical environment, or as some of us like to say, let over lambda. And that's a quote from Doug Hoyt from his aptly named book, Let Over Lambda, which is really just a Lisp community term for a closure. And the thing that I want to emphasize here is a saved lexical environment. Now, don't worry if you don't understand what this means at the moment, because hopefully it'll become a bit clearer as the video goes on. But really, at its essence, a closure is just a saved lexical environment coupled with a function to kind of modify and interact with this environment. So to explain this a bit better, I need to talk about what a free variable is. So what is a free variable? Here I have a function called multiply by, and it has one parameter called x. But if we look in the body of it, it is doing a return x times y. And in this instance, y is considered a free variable, and x is considered a bound variable. Now, y is considered a free variable because it's not an argument to the function, nor is it defined anywhere in the body of this function. And to actually evaluate this, we need to figure out where y comes from. And to figure this out depends on how the language is scoped. So we need to talk about scoping a bit. So what is scope? Scope refers to the part of the program where identifiers such as functions and variables can be accessed. So for lexical scoping, this depends on where the code was written textually, and for dynamic scoping, this depends on the runtime execution of the code itself. For most programming languages, and I mean most commonly used programming languages, lexical scoping has been adopted, so it's pretty much the default. But some instead use dynamic scoping, such as Bash, so it's worth kind of comparing and contrasting the two. I have some little examples here to show the difference between the two. Here's a lexically scoped example. So I have a const message, a function example, and a function caller. Now if I call the caller function, it const message equals hello world, so it creates this variable called message and assigns it hello world. And then it calls the example function. Once we're in the example function, it tries to console.log the message, but it can recognize that message here is a free variable. It's not defined as a parameter to example, and it's not defined in the body of example. So it needs to look elsewhere to try and resolve this message variable. But because JavaScript is lexically scoped, it looks in the kind of parent scope, that is the lexical textual location of message. So it says, okay, we've not found it in the example function, let's go up the scope. And it can see that message is actually defined in the global scope here. And it console logs it, and then it returns to caller. And at this point, it's console logged greetings world. To kind of contrast a bit, I wanted to use a dynamically scoped example, so I'm using Bash, and it's effectively the same code. We call the caller function. The caller function defines a variable called message and says hello world, and then it calls the example function. The example function here tries to echo message, and it sees that it's a free variable, and it needs to resolve where this free variable is going to come from. But instead of looking in the lexical scope, it's going to look in the dynamic scope, that is the call stack. So it actually goes up. It says, did the function that invoked example have a variable called message? Oh, yes, it does. Let's use that. And then it echoes message. And by the time it's returned, it'll have echoed hello world. So this is just to contrast the two. Whenever we talk about closures, we almost always mean lexical closures, but that doesn't mean they're the only kind. You also can have dynamic closures, but they're way less common and a bit unintuitive. They're a bit hard to reason about. So if I move on from here, we can start talking about our first closure. Here we have a function called createCounter, and it defines a variable called state. This is just a counter that can increment and decrement. Then we return an object that has three properties. One of these properties is called current state, and it returns a function that references this state variable. And if you notice here, this is actually a free variable. It's not in the scope of this anonymous function. It's actually in the lexical environment. And the same goes for increment. This is just a function that increments the value and then returns it. And decrement is the same. It just removes one and then returns the state. So now when we actually define, or we call create counter, it captures this lexical environment. If I move back a bit, it captures this lexical environment and it returns functions that can operate on them. And if I just show you an example, it might make a little more sense. So we've created a counter. And now we want to console log the current state. So because it was initialized to 0, it'll return 0. And now we want to console log the increment. So we invoke this function, it increments the state, it returns it. Because the state is 0, it'll increment it to 1, return it, and now its value is 1. And then afterwards we want to decrement it, so it's basically the same thing. We call this decrement function. It decrements the value of the state and then returns it, which sets it back to 0. So you can see here that there's this variable state that's actually persisted after create counter has been invoked. And this is the essence of what a closure is. It's this environment bundled with these functions. What I want to emphasize here is that the term closure refers to a lambda expression that contains a free variable, those things we mentioned earlier, that have been closed over by its lexical environment. So that means they're really just bundled together so that whenever you reference state, it looks it up in the lexical environment, it closes over this expression, hence why it's called a closure. Let me move on just a little bit. So how can closures be used? Closures are incredibly versatile and can be used in a variety of ways, including but not limited to event handlers, state machines, iterators, memorization, data encapsulation, and so on. And it's this versatility that kind of makes them such a powerful programming concept, because they're not really limited to any one language. In fact, they're probably implemented in any language that has first-class functions and lexical scope. So I'll show you some of the examples here. Let's look at an event handler. So up here I have 3 HTML elements. It's a negative. It's a button that when you click it should subtract a value. Here's the value, and here's the plus button. It's really just a counter from the previous example. And if we look at create counter, we've already seen this before. I've added this little helper function called onClick. It just takes an element and adds the click listener, and then once that's been fired, it calls the update function and the render function. So here we initialize the create counter, we get the HTML elements, and then we create a little render helper function, which basically just sets the value of this to the value of the counter. This render call initializes it to 0, and then we add the onClick listener. So we're saying here, add an onClick listener to the increment button, and when this is clicked, call the counter.increment, and then render the result. And then similarly, we're saying onClick, call the decrement button, and when that has been clicked, call counter.decrement, and then render the result. And here's a little example of how that looks. I've added a little bit of styling, but it's effectively the exact same code. This is a helpful little example. So if I go back, the next example I wanted to talk about is a state machine. So here we have a really simple abstract state machine for a turnstile. Now it has 2 states and 2 state transitions. There's a lock state, and then you can change this by inserting a coin, which changes it to the unlock state. And then when it's in the unlock state, you can go through it or you can push, which then changes it back to the lock state. And you can use closures to like model these very intuitively. I'm going to show an example of it. So we have a function here called create turnstile or create TS. And it has an initial state of locked. And we create an object of the states and the transitions that they can have. So if you look here, if we look here, locked, if you insert a coin, can change the state to unlocked. And then unlocked, if you push it, can change the state to locked. And here's where we create the functions that reference the lexical state or the lexical environment. We return a transition function that takes an action. And if it's a valid action, then we update the state and return it. Or if it's not a valid action, we just say invalid action. So we create the turnstile. We say turnstile get the current state, which will just return locked. And we can do console log turnstile.transition coin. So we're inserting a coin effectively. It sees if this is a valid state transition. So it's currently locked. Coin is valid, and it needs to change it to unlocked. So we update the state, and then we return the state. So now the turnstile is in the unlocked position. And now that it's in the unlocked position, we're able to push. So we pass push. We take it as an action. We see if it's a valid action. So it's currently the unlocked state. We're doing the push action. And then we're updating it to the lock state and returning that. So now the turnstile is locked. And this seems like a lot of work to kind of create what is effectively just a state machine that could be probably modeled in a few less lines of code. But this is really close to like a general idea of a state machine, like an abstract state machine. So as an exercise to the viewer, I would suggest trying to create a function that takes an initial state and then takes a set of transitions. And this way you can kind of just build a state machine by passing those two arguments. Okay, so the next thing I wanted to talk about is also an iterator. This example is a little monopoly board. So we have a function called create monopoly if you pass in a monopoly board. And a monopoly board is just an array, and I've only used these few examples. So it might be collect 200, Baltic Avenue, Community Chest, and Boardwalk. So we want to console log the current state, which is the first value, which is collect 200. And then we want to be able to do monopoly.next to move to the next square. So if we go up here, next is initialized n equals 1. So we want to move 1 by default. And we just add the index to the step we want, and then we modulo the board.length. And all this does is make it kind of an infinite loop so that if it overflows, it wraps back around just like a monopoly board does. Now, if we do the next one, it goes from Baltic Avenue to Community Chest. And then if we do the next one, it goes from Community Chest to Boardwalk. And then if we go next to, it actually jumps over to from Boardwalk, collect 200, and then goes to Baltic Avenue. And then same here from Baltic Avenue, if we want to go 3 steps ahead, it'll go from 1, 2, 3, and end at collect $200. So you're probably asking, we already have iterators and generators in JavaScript, like what's the point of this? And for instance, obviously an array is already an iterable, but this is a more general programming concept that can really be applied in any programming language that implements closures. You don't really have to wait for the language designer to implement iterators or generators. You know, if you have this, you're able to do it yourself in a fairly straightforward way. And the last thing that I wanted to really talk about was memoization. So in computing, memoization is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls to pure functions and returning the cached results when the same inputs occur again. So the key thing to understand here is, what is a pure function? A pure function is one that returns the same output given the same input and also doesn't have any side effects. So that is, it doesn't change any global variables or modify any state outside of the function. It's really just like a calculation, so to speak. So I have a little example here of a function called memoize, and this is a higher order function that takes a function, creates a cache object, and then returns another function. Now this ... args, that's just saying create an array of the arguments. And then we convert that array into a string, and we use that as the key in the cache. And if the key exists, it means we've already calculated it with these arguments before. So just return the cached variable, like the cached value. Don't bother recalculating everything. Or else we've not seen this before. So we need to call the function with the arguments, cache the result, and then return the result. So to kind of illustrate this, I have a factorial example. Now this is a recursive factorial, and these are kind of notoriously inefficient, especially in JavaScript. But we can make this a memoized factorial just by passing the factorial function to the memoize function. And just as an example, I've did a memoized power of 2. So if we console log memoized factorial of 100, it invokes this function. The ... args, that'll just be an array with a value of 100. Cache key will now be converted to a string. So the input will be 100. If it exists in the cache, return the cache value, but it actually doesn't at the moment because we've not invoked this before. So what we need to do is apply the factorial function to the arguments, and this is doing the calculation, cache the result, and then return the result. So this first call is the most expensive call. It calculates the number 9.332, etc., times 10 to the power of 157, which is a really large number. And we want to call it again. So when we call it a second time, we can see here it's going to get the arguments, and because of the same arguments that we used last time, it's actually going to be in the cache. So this says, oh, it does exist, just return the cache value, don't bother recalculating everything, especially because this could be an expensive calculation. And this second call will be much quicker. It'll give the exact same result, but it'll just do it in a fraction of the time because you're bypassing that calculation. And if we go to the memoized power of 2, it's doing the exact same thing. It'll get the, 1,000 to the power of 2, it'll return 1,000,000. And then this will be a somewhat of expensive calculation, and then after it, if we invoke it again, it'll just return 1,000,000 from the cache. Very straightforward. It's a very powerful technique, and if you have expensive pure functions, it's really good practice to just memoize them in general. So yeah, that's everything that I wanted to cover. Thank you for watching. If you have any questions, please leave them in the comments below. If there's anything that wasn't really clear, please let me know. And if there's anything you'd like me to cover, I'm open to any suggestions, and I really appreciate you taking the time to watch this. Thanks loads. Bye.